quickly going to set it up in the other room. Okay, very sorry for the delays. I had to teach for the other class in the morning in another building. But we are all set. Oh, no, not for that one. Hey, what's going on here? Okay, let me quickly verify that everyone can hear me at home or whatever you're watching. Yeah, okay, now this is the basic statistics live stream. Feel free to ask any questions. Also post it if the audio is not okay, then I'll try to fix it. We can hear you. Okay, great. Okay, so the topic of today is simple linear regression. This is the last of the simple tests that we're going to do. It's actually already a model, but from next week on, we are only going to expand on this. And everything that we've done so far, we can actually do with regression. But we'll see that in the coming week. So for now, just the introductory lecture to regression on simple linear regression. Take that off. Okay, so first I'll give a quick overview of what simple linear regression actually is and how you can do it in R and how to interpret the output. And I'll also go over the correct workflow. So what should you do first and which steps should you pass before you can actually draw conclusions from the summary table. I will also show how you can interpret the summary table, in particular the estimates, their standard error, the p-value, and R-squared. And R-squared is interesting because it provides a measure of how much of the variance in the outcome your explanatory variable has explained. Now, then we're going to have a short break, and then I'll explain how the we're only going to do the first part. Second part is only for advanced statistics. If you're interested in how the estimates are obtained, it's called least squares, or also ordinary least squares, OLS. I can recommend some books that explain it well, but for the purpose of this course, you don't have to know how it works exactly. Okay, so what is simple linear regression? It is called simple because it only has one explanatory variable. And when we have that, what we're really doing is we're estimating a line, right? So we have an intercept, which is the value of the outcome when the explanatory variable is equal to 0. So that's where it hits the y-axis, so to speak. And we have the slope, which is the increase in the response variable if the explanatory variable increases by 1. So that gives us the entire model already. We have an outcome y, which is the intercept, plus the slope times the explanatory variable, plus some error because, you know, it's just a model. It's wrong, it's just an approximation, and every person will deviate somewhat from this relationship. Okay, this is what that looks like, animated. So here we have an intercept, which is at 3, so that's just a starting point. And the slope is like a staircase, you know, it's every time it's a 0.25 increase if we increase the explanatory variable by 1. Yeah, and the notation for this, the model itself, we put a hat over the y, which means the predicted value of y, because as you can see, the actual observations, you know, they don't all fall on the line. So this is the relationship, but there's still an error. Okay, here's a simple example. Let's say that we have measurements of people's BMI and their body fat percentage, and maybe we want to know, okay, how well do those two relate to each other? Is there a linear relationship between them, and how much of the variance in body fat percentage can be explained by BMI? Because BMI is a lot cheaper to estimate, especially in a large trial, and accurate measurements of body fat percentage are actually quite hard to get. One way is dual X-ray, which again is very expensive. So we enter data in R. Usually you wouldn't do this manually, but it's just to show how many numbers there are. But usually I would just use, for example, read comma separated values. And if you have a Dutch version of Excel, or you have any version of Excel in a country where the decimal separator, so the numbers after the whole numbers, is a comma, then you have to do read.csv2, and then it will work. If you want to know how to read CSV files, I have like a 2-minute video on that, but I'll assume that you are able to read your data in R for now. So we have this data frame with the BMI and the body fat percentage. I think that's 20 measurements of each. And then the first thing you should do in any analysis is to try and make a meaningful plot of your data. Now, for simple linear regression, that's very simple. We just have the explanatory variable. We usually put it on the x-axis. It's not necessary, but you know, this is x, this is y, so now it's the same as in our model formulation. And the outcome, the body fat percentage, is plotted over here. Yeah, you can of course try and make it more readable and remove the box around it. I added some color. It's not necessary, but just try and always make a visualization of your data, because it will immediately tell you a lot about your data, like are there outliers, does it look like there's a linear relationship, etc. Okay, then the next step is to actually fit this model, which is not that difficult. There's a function called LM, linear model, and then you first specify the outcome. So in this case, that's the body fat percentage, because that is the variable we want to know how much of the variance we can explain with BMI. And then we have the explanatory variable, which is BMI. Could you swap these around? Of course, but then your model gives you a different answer. It gives you the answer how much variance in BMI is explained by body fat percentage. And the estimates will be slightly different. Okay, so this I store it in an object with the assignment operator. I call it LM, and then we're going to do a bunch of stuff with it. You probably think that I'm now going to show you what the intercept and the slope is, but actually that's not what I'm going to do. Because linear regression comes with a set of assumptions, and only under these assumptions is inference from this model valid. So the estimates I get, the p-values I get, they are only correct in interpretation if these assumptions are met. So independence just means that you have true replicates, that all your observations come from distinct experimental units. So that you, if you have 10 individuals, that's independent. But if I have 10 measurements from one plant, for example, this is just one plant. It's not an experimental unit, those measurements, so that is dependent. For linear regression, it has to be independent. Once you do the advanced statistics course, we're going to learn how you can also deal with dependent data, because of course there are a lot of scenarios where you need dependence in your data. If you want to know how something progresses over time, like a patient, if you want to know whether tumors shrink or body fat percentage decreases or whatever, you have to keep measuring them. So you have dependence in your data, not part of this course, but you'll learn that in the advanced statistics course. Okay, second one should be obvious. To do linear regression, there should be a linear relationship. The question is, of course, what counts as linear, but we'll see that in a bit. Then we have normality of the error. That is a more important one for the p-values. It means that deviations from the model, so I'm going to go back to this visualization over here. Yeah, we have the data. We assume that the differences from the model are normally distributed. That is what that assumption says. So it means that most observations should be close to the line, fewer should be far away, and a rare few, like this one, should be far away. It also means that deviations in either direction should be equally likely. Yeah, and specifically to follow normal distribution, and we have tools to check whether that is approximately correct. Okay, so that's normality. Then we have one more assumption, which is the least important, but you know, it is nice to have, which is constant variance of the error. Now, what does that mean? We're going to go back to this figure again. It means that if I go across this line, then the extent to which observations differ from the line should not change. So if they change like this much over here, they should change by the same amount over here. Yeah? That's what constant variance means. Okay, those are the assumptions. There is another thing that we check for using diagnostics, which is observations with high leverage or observations that are outlying. There is no such assumption as there are no outliers, because if you assume something comes from a normal distribution, the normal distribution goes all the way to plus and minus infinity, so that assumption makes no sense. You can have an outlier due to sampling error. It can happen. But it can have an extreme effect on your estimate. It can affect your estimates more than you want it to. So we do check for outliers, and if you have reason to remove them, we can do that. If we don't have reason to remove them, there's something called robust regression, which works well even with outliers. It's not part of this course, but point being that it can really affect the intercept and the slope and the p-values, so we do check for it. Okay, we've already seen some of the model diagnostics for Anova. This is going to be almost the same. Next week, we're going to talk about multiple linear regression. It stays the same. These plots are going to keep coming back, and they're going to keep looking more or less the same, which is really important, because let's go back a couple slides. We have this model, right? This one. And we can just kind of see whether the assumptions make sense. Independence, okay, I cannot see that. I have to know whether these are independent observations or not from the study design, right? But we can see that, okay, that is probably approximately normal. You know, at least it's symmetric, the differences from the line, and further deviations are rare. We can see that the variance is not really decreasing or increasing, so I don't see any problem. So what's the point of these diagnostics? That will become very clear once we get to multiple linear regression, because for two directions already harder to visualize, but if you have a hyperplane, so if I have 3 or 4 or 5 explanatory variables, it is impossible to plot. So that is why we use diagnostics. We're just going to take those residuals, so those distances to the line, and we're going to check on those whether the assumptions are reasonable. So that's what we're going to do now. I have another lecture on this later today where we go a little bit more in depth. I just want to quickly show it again, looks similar to yesterday. What we need for this is called the residual. That is this, is the vertical distances to the line. Why vertical? Because that's the outcome. We want to know the error in the outcome, yeah? So we take those red lines and they represent positive and negative numbers, right? It's the distance to the actual model. Some are negative, some are positive. Now, then we could create some sort of histogram. It says histogram, it's a density plot. Point being, you could try and plot this, but it's kind of hard to see, okay, is this, it's not normal because there's a bump over there, but is this approximately normal? That is a very hard question to answer. So we use a different kind of plot called a QQ plot. That's this one. And in this plot, the quantiles of the normal distribution, or the t distribution, are plotted as a line over here. And then it's very simple to see, is this approximately normal? Because deviations from this line are deviations from normality. And if we use this nice version of the plot from the package CAR, Companion to Applied Regression, which is a book, then we even get confidence intervals, and we can get a very nice idea, is this approximately normal, or is this beyond the 95% confidence interval of where we would expect the values that come from a normal distribution. So that's this one. Let's look at the other ones. What does this say? Does anyone know what any of these say? Anyone have an idea? Yes?
So like something about the variance, if it's equal, but we're not looking at different groups, are we? No.
Yes, but it is an assumption. Okay, so what are fitted values? Does anyone know? It was correct, by the way. Okay, let's take another step. Oh yeah, go for it.
So the fitted values would be the red line, so it's basically you're averaging your observations, aren't you?
Okay, this red line is just a smoother. It's just a lowest line, but for now we can ignore it. The fitted values, we'll go back again to this one. These are the fitted values. It is what the model predicts an observation to be at if we ignore the error, right? So it starts at 0 and it goes up to here and up to here. Now, what do we do then? It's a lot easier to judge whether a relationship is linear or not if we just remove the linear effect. So we subtract the intercept, so it starts at 0, right? And we subtract the slope everywhere, so now the line is not like this, but it's flat. Now it's on its side, it's at 0, so it's very easy to see, okay, is there any relationship left in these data after I subtract a linear relationship? And if the answer is yes, then there is not a linear relationship but something non-linear, maybe quadratic or logarithmic, and you could try transformation, which we will come back at later. What you can also do with this plot, as she said, is to see whether there is a deviation from this assumption of constant variance. If there is constant variance, then we would expect the same spread over here as over here. Now, there's one problem with checking for constant variance, and that is that if you have more samples, there's a bigger chance that one of them is far away. So if you, let me just draw that. If I have a relationship like this, so flat again, and I have samples over here, 1, 2, 3, and I have 10 samples over here. These could have the same variance. These are just fewer samples, so the chance of getting one far away is just rarer, right? If I have 10 samples, I have 10 chances to be far away, so you're gonna see a spread like this, a cone shape. But that doesn't mean there's non-constant variance. So this one is mainly for checking linearity. This one is for checking whether the variance is constant. You can do it with this if the number of observations everywhere is more or less equal. But with this one we do a transformation, so we take the square root of the standardized residuals. Standardized means that you subtract the mean and divide by the standard deviation, and then it will always have the same standard deviation of 1 and it will be centered around 0. You take the square root of the absolute value of that, y, so that they're all positive, and so that you can simply look, is this line going up or is this line going down? And if that's the case, there is a problematic non-constant variance. If that's not the case, no problems. In red, we see a smoothing line, right? In this one, in this one, in that one. That's just a moving average. It's a very simple nonlinear model to see, okay, where are the points more or less going? It has no special meaning. What you're looking at is your data, that's the black points. But sometimes it's easier to, see, okay, where's the average of my data? And then you can see, is this constantly going up or is it constantly going down? And if yes, there's a problem. It is standardized, so you can look at the actual values. If it's not that much, then you can ignore it. If it's very clearly steeply going up or steeply going down, then it's a problem. Okay, last one. Anyone remember what that one is for?
For outliers?
Yeah, exactly. So here we have two different measures. We have the standardized residual. If those are very far away, the observation is outlying because it means it's very far from the model. And we have the leverage. Now, anyone have an idea what leverage might be? I'll give you a hint. The name kind of says it. What does the English word leverage mean? Yes.
Is the effect a single center observation can have on the mean of the overall?
Exactly. It's the effect that one observation can have on the entire line. Now, if you have high leverage, think of a children's play garden, and I don't know what it's called. It's the thing where two people sit on either side and it goes like this.
Seesaw.
Seesaw, thank you, yes. high leverage is like if you were very close to the center of that seesaw, then you know it's going to have a different effect than if you're on the outside of the seesaw, right? If you're very far away, then your effect on bending the seesaw is very, very large. Same thing in regression. If you are very, very far away from the model and you're far away from the middle of the observations, then you pull really hard on the estimates and the line will be in your direction. If you're very close to the average of the observations, okay, the intercept might move a bit, but it doesn't have much leverage because the seesaw doesn't move, right? So that's leverage. Okay, so let's do a quick quiz what violated assumptions look like. This is one example of violated assumptions. Let me make it slightly bigger. Anyone have an idea which assumption is violated here? I'll give a hint. Only one is violated. Yes?
If it's the last plot, plus distance versus leverage, looks a bit odd.
Yeah, it does look odd. Over here we have an influential point. So later we will see what it looks like when you zoom this plot out. There are two boundaries. One is at 0.5. It's really small, sorry for that, but this says 0.5. If it's beyond that, that's anomalous, so strange. Not necessarily a problem. If it's beyond 1, then it's statistically outlying, so beyond the second border. And then you really have to consider, okay, do I still trust the p-value or should I use another method? The problem is when one assumption is violated, all your plots will look funny. So in this case, I simulated a quadratic relationship. And you can see that even if I have a linear relationship in the data and I subtract that, there's still this parabolic shape left. Now, why is that? It's because the actual relationship is like this. So I can fit a line through it, but still, you know, observations over here are going to on average be more over here, and the one at the corners are going to on average be more over there. So yeah, this is an example of non-linearity, but the problem is, if you fit a linear model, if you would only look at this plot, yeah, this number 19, also very small, sorry, but that's the observation all the way over here, is also this one. It's just the observation that is the furthest away from your model. There's always going to be one observation that is the furthest away, right? So it's kind of hard if you only look at one plot to see what's going on. So that's why also in the assignments, etc., I always plot all four at the same time so that you have a complete overview of what is going on. Now, a clear trend in this residual versus fitted plot, sorry, it's been a long morning, means that there is something left that is not linear. So this is an example of violation of linearity. Okay, next one. What's happening in this one? Which plot? Yeah, there's a steep increase. So this data is definitely heterogeneous in variance. So there's definitely non-constant variance. What else? What about the QQ plot? Yeah, and not just, you know, one observation or something, but this entire gap here. So you would expect, yeah, less values to be here and more values to be here, so that they all go over here. So, what is going on? What causes a gap like this? Well, we can kind of see it over here. We see some observations here and some observations here. This is actually a binomial outcome. This is the last topic we will discuss, generalized linear models. These are data that do not come from a conditional normal distribution, but this is the number of successes out of a number of trials that can only take on certain outcomes. You know, you can only have 1 success, 2 success, 0 success. So you see this really big gap. And in general, when you see a staircase like that, it's either because your data were rounded or because your data come from a discrete probability distribution. Yeah, so this is an example of non-linearity, non-normality, but I just want to show you how difficult it is if you would only look at one plot at a time, because they all look weird, right? Okay, this one is okay. This one, there is non-constant variance, but it's caused by there only being two different possible outcomes. This is binary data. So that one too, yeah, looks like the line is going down. And then there are a couple of points above it only. That's because there are only two outcomes in this data. Okay, then this one. What's going on with this one? Yes?
The unequal variance.
Yeah, how can you tell?
The top left you see it starts with a small or small and then goes wider and wider, and your bottom left goes up.
Yeah.
Yeah.
Okay, let me quickly draw what he said. Okay, here we have the residuals versus fitted plot. When there's non-constant variance, you will usually see a kind of cone shape, like this, you know, like a trumpet. Why? Because that means that at one point, at one end of the spectrum, the variance is very small, so observations do not differ much from each other. But as we go to larger values of the explanatory variable, then also the spread of individual measurements becomes larger. Yeah, like I mentioned before, the non-constant variance assumption is the least important. Your p-values are still correct. It's just linear regression is not efficient when this is the case. So there are better methods. Okay, you can also see it here. Because like I said, what if I only have one observation here and I have 100 over here? Not the case here, but suppose. Then you would also see this cone shape, but it's just because you have fewer observations, and if you take more samples, there's a bigger chance that one of them is far away, so you have more variance. So this is the more objective way of seeing it. There's a very clear upwards trend, and it spans more than 1 on this standardized scale, so this is definitely non-constant variance. Okay, then this one. What's going on with this one? Yeah, how do you know? Yeah. So this is not just an outlier, this is a high leverage outlier. This is the most problematic case. So on the x-axis of the Cook's distance versus leverage plot, we have the leverage. So that is the extent to which it affects the estimates. Yeah, so if this is large, it will pull really hard on the estimates. If this is small, then okay, it might be outlying, it doesn't really matter. This is beyond the bounds of this figure. And if it's beyond 1, then it's statistically outlying. So this is really well, not necessarily negatively, but it is affecting your estimate. So you should be aware that one observation is very strongly affecting your conclusion. You can also see it over here. There's one observation very far away from the rest that doesn't really follow the trend of the rest. And we can also see it over here. It looks like the variance goes up, but that's really just this one observation that is causing the variance to seem higher because it is the only residual over there. And you can see it in the QQ plot. We see all observations like this, and then we see one that is really far away and outside the confidence intervals. So yeah, this is what a problematic outlier looks like. Okay, so then of course, what do you do if there's if the assumptions aren't met? If your observations aren't independent, then you can't use normal linear regression. You need a mixed model. If there are pseudo-replicates, you could average your pseudo-replicates. It's not the most efficient way, it's better with a mixed model, but it is valid. It will give you correct inference. And if you have repeated measures, spatially correlated observations, or other kinds of dependent data, then you should really look into mixed effects models. If normality is violated, then okay, there's two things that could happen. Either it is just not quite normal, but it was a reasonable assumption, or normality was never a reasonable assumption in the first place. Let's say you have count data. We know certain distributions that are suitable for count data, like the Poisson or the negative binomial. So you shouldn't be using normal linear regression anyway. You should be using a GLM, yeah, or this is a generalized linear model. This is a generalized additive model. These we don't cover in the course. This is the last subject you will get. yeah, if normality is otherwise violated, it is hard to see how bad is too bad. So I wrote about that in the book. You can have a look at that. In the first book, there's a chapter called "Is My Variable Normally Distributed?" If it is really non-normal, there are methods that don't assume normality. Yeah, but we don't. We do cover the ones for Poisson and for binomial and for negative binomial. That's in the lecture on GLM. But if it's none of those and you don't know why it's not normally distributed, it doesn't happen often. Maybe you forgot a certain confounding variable, and maybe you just need a different method entirely. Okay, what if non-constant variance is violated? If the variance increases over time, over the explanatory variable, then usually the relationship isn't actually linear, but it's probably log linear, logarithmic. Or it could be that if you transform your response variable in a certain way, that suddenly there is no non-constant variance anymore. So that's one thing that we will look at in this course. Another thing is you could consider using robust regression, which is a method that is very non-sensitive to outliers. So even if the variance increases, it will still give you good estimates. But if all else fails, non-constant variance is the least important assumption, and your model is still valid. So you can use it, just be aware it is not very efficient. Then, if you have a problematic outlier, most people would immediately remove it to see what happens, but this is very rarely the right thing to do. Almost always you should either just accept that this is part of the data generating process and just leave it in, or you should use robust regression, which is that method where it's not so sensitive against outliers. But there are exceptions. If you see one person in your data set that weighs 1,200 kilos, probably the decimal separator was misplaced, right? Or if you see a value that is just completely unrealistic, then you can take it out. Maybe it's just not recorded correctly. Then the other thing is, if you have valid reason to assume that this observation is different from the rest. So let's say there was an error in experimentation. Yeah, let's say that you are doing PCR and one of the vials you forgot to put in the fridge, or one of the vials you dropped. Then okay, if then at the end of the road it's an outlier, then you leave it out, right? Because that's not representative. This is one reason why keeping a lab journal can be online for all I care, but keeping notes of everything you do right and everything you do wrong is really important, because then you have a good reason to take out an outlier. Okay, then assuming all the assumptions were approximately met, then we can actually look at the output of the linear model, and that's what I'm going to explain now. Is this readable? Okay. I will also say it out loud if it's a bit small. Is it too small? No. Okay. So here we have summary of LM. If you remember, I said LM is body fat percentage as a function of BMI. So first, it's very nice to me. It says back to me what I did. You very rarely need this unless you're fitting a lot of linear regressions. You want to be like, wait, which one am I looking at? Then it's useful, otherwise not really. Then we see the residuals. We see the minimum value, the maximum value, and the first 25, 50, and 75% of your data. This can be used approximately to assess normality. If the error is normally distributed, then you would expect it to be a distribution with one peak, right, and symmetric. If that's the case, then the median is the same as the mean, so the median should be 0, because on average the observations fall on the line. So you can check if this is very far away from 0. In this case, not really. Then, if a distribution is symmetric, then the first 25% and the last 25% should be more or less the same distance away from 0, right? So you can do that with the first and third quartile. Then, if the maximum is really, really large and the minimum is not, then maybe there's an outlier. So this is a very crude way to do what we've been doing over here. This is a much more principled way, so in my opinion, you can completely ignore this and just do diagnostics. Yeah, so that's two things you don't need. And then the thing you do need, this is what it actually estimated. We have an intercept and we have a value for BMI, that's the slope. So this model says that body fat percentage is 0.02, that's the intercept starting point, plus 0.99 times BMI. So it says for every unit increase in BMI, you would expect body percentage to go up by 1%. So that means a 1 millimeter increase in BMI, 1 millimeter, okay, that doesn't sound quite right. So an increase in 1 corresponds to a 0.99 increase in body fat percentage. In theory, you know, you can extrapolate with a model, dangerous business, but if there would exist a person with a BMI of 0, then they would have a body fat percentage of 0.02 according to this model, because, you know, we just multiply 0.99 times 0. And this model says something else. It says residual standard error. Okay, this one we don't need until multiple linear regression, but this one is interesting. Multiple r squared, that is the variance explained by this model. So apparently, if you know someone's BMI, you know, given that the results of this experiment are correct, then you can explain 39.7% of the variance in their body fat percentage. So it tells you something about how strong this relationship is. If it's like 99%, then the relationship is very clear. There are very small deviations from it. This one explains 40%, which, yeah, is that a lot? Is that not a lot? I don't think it's very much in this case, because that means that there's still 60% of variance unaccounted for. So yeah, maybe you cannot just replace body fat percentage measurements with BMI, if that was the purpose of this study. Now, it says something else. These are estimates. So this first column over here is what you would look at first usually. Then the standard error is a measure of uncertainty. So yeah, okay, this 0.02 is the estimate, but actually the standard error is quite large. So it doesn't necessarily have to be 0.02. It could be a slightly different value. And because standard error is so big and the estimates so small, yeah, if you divide an estimate by a standard error, that's a one sample t-test. Because we're comparing its mean to 0. So that gives you a p-value. And that p-value tells you, is this estimate significantly non-zero? Now, it's a bit unfortunate that the default is to include this p-value for the intercept, because very rarely is this relevant information. You know, is it important to know that if your BMI is 0, that your body fat percentage does not differ significantly from 0? I don't think so. But this one is interesting for BMI, for the slope. Because what does it mean if the slope is significant? Anyone have an idea?
That there's a relationship between the BMI and the body fat?
Yeah. So if the assumptions are met and you have a significant p-value for the slope, then your conclusion is there is a significant relationship between BMI and body fat percentage. That's what this p-value tells us. Yeah, so again we have estimate, standard error. If we divide the estimate by the standard error, it gives us a t-value, and it corresponds to a p-value. Now this p-value is quite small, so you could conclude that there is a significant effect of one on the other. Yeah, or in other words, there's a significant linear relationship between the two. Okay, when you're done, you can plot your model. So here I've added the line that was estimated. This can be done very simply. So the plot is just body fat percentage tilde BMI, so body fat percentage as a function of BMI from the data frame df. Then you can say AB line, A is intercept, B is slope in this case, and coef, or you can type it out, coefficients, LM. R knows what to do with this, so if you do this for a simple linear regression, just these two lines, that will give you a plot with your data and a line going through it showing your model. Then I've added a text here. This, you don't have to know this by heart, of course, but this just shows you how you can get nice scientific notation in R. This is what the R squared is, because that's nice as a little extra to show, okay, this is the line, and it explains 40% of the variance in body fat percentage. Okay, it's actually not that hard in R to also get a prediction interval. A prediction interval is not the same as a confidence interval. A confidence interval tells you something about the precision of your estimates. A prediction interval tells you where you would expect observations to be. And that is a very interesting interpretation, because then we can say, okay, if we calculate a prediction interval for every point from here to here, then we can say with 95% certainty, where do we expect observations to be? Yeah? So 95% of the future observation should fall within those bounds. Now then we can again see how useful this model is, because actually your body fat percentage can differ quite a lot for your BMI, and the reason is of course that BMI does not take into account fat, it's just length and weight. So if you're a bodybuilder or something, then you can also have high BMI and still have a low body fat percentage. Okay, quick summary. We enter data in R, can be any method that you know of. Then I would always start with plotting your data. Also, if it's not linear regression, always try and visualize it. It gives you a lot of information, also whether your data are read correctly into R. Then fit a model with the LM function. Then perform visual diagnostics. And then check the regression table if the assumptions are reasonable. And when you're done, certainly for simple linear regression, I would plot the model because it's quite simple, and then write a conclusion about it. Yeah, that's the end of this first lecture. I will show the exercises of today. We are now at chapter 7. So this is the lecture I just gave, and here are the animations. Here's the code from the lecture, because I understand it's not nice to type over code from a slideshow. So you can just copy it from here and repeat the steps that I did. Then the exercises works the same way as some of the previous ones, where you can download them by clicking on it. And there's also a PDF version, where you can see what it looks like rendered. So yeah, just try and answer these questions. I'll give you a very important hint. This will almost certainly be on the exam. A question like this. So being able to tell what one value is if you know the other values of the coefficients table, because it shows that you understand how to read this table. Also, what is the variance explained in this model? That's also something you should recognize. Then question 2, question 3, we're just fitting more linear regressions, because doing it once doesn't really give you an insight into what the diagnostic plots look like, etc. And then, there is a hard question. This will definitely not be on the exam, something like this. But it is a nice challenge for you to look at. Here's also a hard question. When you see those and you're not able to solve them, don't feel stupid. You don't have to have this level of understanding. Okay. When we're done with all that, this one we don't have to do. I will give a lecture on model diagnostics, which also has some exercises. But seeing how we're a bit late today compared to other days, after the model diagnostics lecture, I will leave these exercises for you to do after I'm done. And you can go home if you want. It's Friday, but after the second lecture, I will do a wrap-up of the first 2 weeks, and we will cover the methods that we've had. And if you have questions, now is a good time, because if we're all up to speed with the methods so far, then it's going to be a lot easier once we get to the interesting models of next week. Yeah? Any further questions? Okay, if not, the room over there is also open. You can sit throughout the building if you want. I think I'm alone today, so I will put my stuff over there, and then I will walk around and answer your questions. Good luck with the practicals.